Another browser window over here. Hold on a sec. Close this. Close this. Don't need that right now. Okay, so I'm gonna try to solve a couple of LeetCode problems. Let's see. Problems. Amazon. Hold on, let me just correspond to a DM. Great stream so far, right? Literally just the streamer staring at his phone. Okay, let's see what we have here. Sort by frequency? Yeah, that sounds pretty good. Sort by frequency. I'm not really looking to start with the hard. Maybe I'm probably gonna try to do like some medium challenges that have a reasonable acceptance rate. That seems like a good way to start. Or maybe just start with an easy problem, maximum units on a truck. Let's see what this is. Easy with 74% acceptance. Ideally, I should be able to knock this one out pretty quick. Okay, so you're assigned to put some amount of boxes onto one truck. You're given a 2D array box types where box types I is the number of boxes and the number of units per box. Number of boxes is the number of boxes of type I. Number of units per box is the number of units in each box of type I. You're also given an integer truck size, which is the maximum number of boxes that can be put on the truck. You can choose any boxes to put on the truck as long as the number of boxes does not exceed truck size. Return the maximum total units that can be put on the truck. Okay, so in the example, we get box types. So 1 box with 3 units per box, 2 boxes with 2 units per box, 3 boxes with 1 unit per box, truck size 4, output 8. There are 1 box of the first type containing 3 units, 2 boxes of the second type, 3 boxes of the third type that contain 1 unit each. You can take all of the boxes of the first and second type and 1 box of the third type. Oh, interesting. Okay. So the truck size is the number of boxes that can go on the truck. So it seems like we just want to try to yeah, this just seems like a greedy solution where we just sort the boxes by the amount of units in each box in descending order, and then we just kind of take them, take as many as we can. So what we can do is box types dot sort. We got box A and box B. Box A and box B, and we just want to sort by the number of units per box. So we want to return, we want to sort in descending order, so it would be A sub 1 minus B sub 1, so sub 1 being the number of units per box. And then while let's see, while truck size, so while we still have room left on the truck, So this loop will keep running as long as truck size is greater than 0. What we'll do is, I do actually just want to log this just to make sure I did that right. Console.log box types. Comment these lines for a second. So yeah, that worked. So yeah, it went from, it kind of looks like it just reversed the array. It basically, in a sense, did, but that's what we would expect to see there. So that's good. So then we're trying to calculate the answer, which is the answer, which is the maximum number of units that we can possibly do. So while there's still room left on the truck, so well, there is actually an edge case here, which is if the truck size is larger than the total number of boxes we have, then everything just goes on the truck. So this while loop, in that situation, this while loop would not terminate. So I think we can just check that first. So for example, let's see, const total boxes equals box types dot reduce collector, and then we've got the box and we have the number of boxes here. In this case, and then yeah, we might as well just do the math here as well. So we'll just do n boxes, n units, like that. And we'll start this off as 0. Oh, actually, you know what we can do is we can have we can do total boxes like this. Total units will just be, we're reducing into an array of two variables. Reduce, extremely powerful function, and it starts off at 0, 0 like this. And then what we want to do is collector 0, which is the number of boxes, the total boxes. We just increase that by the number of boxes. And then collector 1 is increased by the number of boxes times the number of units in each box. And then we return the collector. I think that should work. And so basically what we can do now is we know the total units that we have overall in all the boxes. And so if the total boxes is less than or equal to the truck size, then the total units is just the answer. So if total boxes is less than or equal to the truck size, we can just return total boxes or total units. If that's not the case, if we have more boxes than we have room for in the truck, then we need to take the best boxes. So we start off with our answer of 0, and while there's still room left in the truck, what we want to do is, so box types is already sorted, so we just want to go for the first thing in the box. There's probably a really fancy way to do this, but I think a simple way to do it would just be to do truck size minus equals box types sub oh, you know what, we can do this a little. So I'm going to change this to be sorted in ascending order by number of units, because then we can remove items from the end of the array in constant time. Whereas, because that's kind of what I want to do, I want to take like the largest box, add the units into the answer, delete that box. If there's no boxes left of that type, I want to remove the box from the array. And because we already checked this condition here, I don't think we'll run into any edge cases. So minus equals box types sub box types dot length -1. Oh, actually, all we do here is minus equals 1, and then we want to increase the answer by we want to increase the answer by the number of units in the largest available box. So that would be this index 1 of the box, because we have the number of units. And then lastly, we want to decrease the number of boxes of that type that we have. So we would have box types sub, yeah, it would be the same thing. We just grab this, put it here, and we would subtract, we would take the first, we would take the first element of that and subtract 1. And then if we now have 0 boxes left of that type, if box types dot length -1 sub 0, if that's 0, then we can do box types dot pop, which will just remove the last element of the array. So without double checking this code, let me just run it. And we got a wrong answer. Yay! Okay, so what happened here? I messed something up. I output 5 and the correct answer is 8. Can I set a breakpoint here? I don't know, does LeetCode have debugger now? Can I just do this? I don't think it does, that'd be too fancy. It's been a while since I've done LeetCode, so I was just checking to see if they had any new features. So we're outputting 5, so it's definitely not, hold on, let's just see. Let's just see what we get for this, to make sure this is right. Total boxes 6, total units 10, and that looks right. Oh yeah, it's right, because we have 6 here. We have 6 in those two, and we have 4 in the middle. So this part is correct. So then something's wrong with this logic right here. Let's see. So while we have truck size remaining, we're going to put a box on the truck. We're going to update the answer by taking the largest box, increasing it by the number of units in that box, and then we decrease the number of instances of that box that we have. Then if we have 0 of that box left, we just remove it. So I think the move here is to just log the box types array after each iteration of this and see what we're getting. Let's log the answer, the box types, and the truck size. Let's see what we get. So after the first iteration, the answer is 1, 0. Oh, is this not sorted the way I thought it was going to be? I guess it is A minus B. There we go. So we got output 8, expected 8. So let me remove this log, and ideally what you would do right now is run the code on some more test cases. I feel pretty good about it, but okay, let's just do this other test case. So these numbers, and then 10 as the truck size. Okay, we got 91, so I'm just gonna submit. Okay, cool. We got accepted, faster than 36% of submissions. The way that I could speed this up a little bit is if there's truck size left, instead of just adding one box to the truck at a time, I could instead essentially like take as many of the largest box type as possible and throw it in the truck as long as it stays within the limits of the truck size. And then I could decrease truck size by more, you know, like let's say that there is, let's say truck size is 3 and the largest box has, we have 3 of the largest box left. We don't have to add one of those boxes to the truck at a time. We could just add all 3 of them, and that would change the math here a little bit. You know, why don't I just do it? Let's see how much faster we can get this to run. So while there's truck size left, truck size, so the number of boxes we're going to put on the truck, num loaded. So let me just stick with my naming convention. N loaded, right? It's going to be the minimum of the remaining truck size and the number of boxes of the largest type that we have. So I mean, I just gotta keep copying this right here. 0, like that. So basically, we could have like 3 of the largest box left, but only room for 2 on the truck. So this makes sure that we only load as many as we possibly can. So then after that, actually, I think the code can be updated fairly straightforwardly. So I can decrease the truck size by the number of loaded, increase the answer by the number of units in those boxes times the number that we load, and then decrease the number remaining by the number that we load. Does that still give us the same answer? Oh, math.min, obviously. Okay, so that still works for the 2 test cases. Oh, that made it run slower. No, it didn't. Yeah, I kind of wish that LeetCode would like somehow improve the consistency of their timing, but that's fine. So it looks like this does actually run faster. If I like rerun it a couple of times, you can see I basically went down from 130 milliseconds to about like 80 to 90. And now I'm faster than like 70% of JavaScript submissions. Okay. After I finish writing a solution, I do just like to delete the comments because they don't need to be in there anymore, really. All right. So, the game recommends, LeetCode recommends maximum bags with full capacity of rocks. I don't know if I'm quite ready for that yet. And I'm saying that without even having looked at what it is. So let's just go back to the list of problems and see what else we can find. But that was kind of a nice little one to start with. I do hope to solve one slightly more challenging than that. Okay. What is this? Also, did it just switch to like dark mode randomly? Okay, there we go. So we want tags, we want Amazon, and then we'll filter out the solved problems and look at the sort by frequency. That's what I'm gonna do. It's not even gonna let me do that. I can't filter out solved problems, but that's fine. Ooh, LRU cache is actually a problem that I want to solve again because I've written an LRU cache a couple of times, but it's always a good idea to kind of refresh your memory on exactly how the implementation looks. So I might come back to that one at some point. Alright, let's see here. Sum of subarray ranges. Medium difficulty with 60% acceptance rate and a really high frequency. Let's take a look at it. I'm a little intimidated by the name. Pardon me. So you are given an integer array nums. The range of a subarray of nums is the difference between the largest and smallest element in the subarray. The range of a subarray is the difference, okay, between the largest and smallest element in the subarray. Return the sum of all subarray ranges of nums. A subarray is a contiguous, non-empty sequence of elements, right? So I feel like this problem shouts sliding window at me. Because there's a lot of subarrays, right? There's basically n squared subarrays. And so if we were to do a sort of a brute force solution to this, to iterate over all the starting and ending elements of the subarrays would take n squared time. And then if we wanted to identify what is the largest and smallest element in each of those, we would then have to iterate through the subarray. So we'd be looking at n cubed time. And let's see, what are the constraints? So there's going to be 1,000 numbers in the array. So 1,000 cubed is 1 billion. Really? Isn't that pretty quick? No, it's gonna be too slow. I mean, obviously, since it's medium, it's obviously not going to accept brute force. So we're gonna have to do this in either n squared time or better, or like n squared log n, something like, maybe n log n. It's probably going to end up being n squared. So you're giving an integer array nums. So basically what we want to try to figure out how to do for this problem is we want to try to figure out how to, as we're exploring new subarrays, reuse information from the previous subarray so that we don't have to iterate over the subarray to figure out what the largest and smallest is. So for example, let's say that we're looking at a subarray from point I to point J, and let's say that we already know for this subarray from I to J what the maximum and the minimum is, then as soon as we go from I to J to a new subarray, I through J plus 1, all we're doing is we're adding one new element to the array. And so we then need to recalculate what the max and the min is. But in order to do that, we just have to compare the new element to what we currently know of the max and the min from the previous subarray, I to J. So I'm trying to figure out how that... I mean, will that just work? I kind of want to do this one in C++. Oh, long. Oh wait, it's still just 10 to the 9th. So I don't know why they made it long, but that's fine. Oh, it's long because we're returning the sum of all subarray ranges. So I guess we have long answer and then return answer. Man, look, we're so much closer to solving the problem. Trying to think here. So, hypothetically speaking, I think what we want to do is, I've never solved this problem before, and I feel like this type of problem I'm weak at. So, this is going to be a little bit of just ideation here. Like, this is what I'm writing here is not intended to be thought of as final code. And a subarray range, a subarray can also be of size 1. So basically, the answer is going to include just, in addition to everything else, it will include the sum of just all the integers in the array. Okay, so what I'm thinking is I represents the first index of the array that the subarray that we're looking at. And so we have I go from 0 all the way to the end. Then j represents the end of the subarray. So for int j equals I, and j is also less than nums.size. Plus j. So this is n squared, but I think that if we can solve it in n squared, I think that we'll be okay. I think. I could be wrong about that. So I goes from 0 to nums.size, and then j goes from I to nums.size. And so I and j are the starting and ending element of the subarray. So in the case of I equals j, we would be just talking about a subarray that's one element long, which would, and then obviously the difference between the largest and smallest element in that subarray, it would be 0. So we don't actually have to do anything specific for that. We do want to start the answer off at 0, obviously. Okay, so you know what? I still think this answer might be too slow, but I'm going to implement it anyway, or I'm going to try to implement it. So whenever we start off, whenever I moves to a new index, we're looking at a new set of subarrays that are starting at I. And so we know that the max and the min is just I. So int max equals nums_i int min equals nums_i. And then for each j, what we want to do is we want to update. Okay, so I think I can't call it max and min, right? Because those are predefined. We'll do max and min like that. I think. So for each j, what we want to do is we want to update the max and min to take into account the new element that we're adding to the subarray. So in the case of I equals j, it doesn't really matter. I could probably actually start off this at I plus 1, but it's not really going to make a difference, I don't think. So max is going to be the max of max and nums_j. And then min is going to be the min of the current min and nums_j. And then answer is increased by max minus min. Is that it? Oh, answer. Sometimes I just call that variable ans. Okay, so for the 3-element test case, we got the right answer. Oh, these can be negative, but I think that's fine. I think my code accounts for that. So let's put the other test cases in there. We get we get 4459. 4459 is the answer to the test cases that were provided. Oh, follow-up, can you find a solution with linear complexity? Okay. So I'm assuming that my n² solution will be accepted. So let's try it. Okay. So n² does get accepted for this problem. However, apparently there's a linear time complexity version of this. So how do we do that? So the largest number in the whole array is going to be the largest number of all the subarrays that it's in. Which is a bunch, like every single element of the array is in a bunch of subarrays. If you think about it. Not all of them. Like if you take like this array, here let's just take this third test case here. If you take this third test case, so the number 3 is the smallest element, so the number -3 is the smallest element of the array. So every single subarray that -3 is in, it's going to be the smallest. And -3 is actually in all of the subarrays, except for the subarrays on the left side and the subarrays, the subarrays that end on the left side of it, and the subarrays that start on the right side of it. So I wonder if we can use that somehow. I think we can. Because if we just iterate through the array one at a time, and so it would just be I goes from 0 to nums.size, then -3, let's say that I is equal to 2, right? So we're currently looking at -3. We know that -3 is the smallest number in all of the subarrays that it's in, but what if we're keeping track of the smallest and largest numbers on the left side as well as the smallest and largest numbers on the right side of the current index that we're looking at? And that's pretty easy to do, because we could pre-process the array and compute that, right? We can iterate from the start to the end, keeping track of the smallest element we've seen so far and the largest element we've seen so far. And then we could do the same thing in reverse, from the end of the array to the beginning, keeping track of the smallest element we've seen so far and the largest element we've seen so far. So then when we're looking at this -3, we know what the smallest number on the right side of it is. We know what the smallest number on the left side of it is. So this is all, I think this is all valuable insight, but how do we use that to actually get to a solution now? I'm quite happy with my n² solution, but hold on, let's just try to figure this one out. I do think we're going to want to pre-compute what the largest number after every index is and what the smallest number after every index is. And the same thing for largest number before each index and smallest number before each index. I feel like having that information pre-computed, which we compute in linear time, I think that's going to help us with this. So if I'm looking at index 2 and I'm at the -3, I know what but what about like this subarray, like 2 through 4? Obviously -3 and 4 are the largest and smallest, smallest and largest, just from looking at it. But there's some optimization here that utilizes the fact that like large numbers and small numbers are the most important like numbers in the array. They basically just they kind of make everything else like not even worth looking at, you know? What if we flip the problem around, and as we're iterating through the array I equals 0, I equals 1, I equals 2, what we're actually keeping track of is I is the end of the subarray. I is the last index in the subarray. This is tricky. Other hints? Can you get the max or min of a certain subarray by using the max and the min of a smaller subarray within it? Yeah, I mean, that's kind of what this solution is doing. But it's also recomputing information needlessly, obviously. So the problem with the brute force solution that I have right now is that whenever I goes from like 0 to 1, for example, we're kind of starting from scratch. Whereas, and we're recomputing a bunch of maxes and mins that we already knew, right? Potentially. This is tricky. Okay, I'm sorry. I'm looking at the second hint. Notice that the max of the subarray from index I to j is equal to the max of the subarray from I to j minus 1 and nums j. Yeah, that's what my code is doing. These hints are trying to lead you towards the n squared solution, which I already have. What are the related topics? Let me guess. Dynamic programming. Monotonic stack. Interesting. The hint is monotonic stack. Okay. I don't actually know what that is. So let me look that up. Monotonic stack. Monotonic stack algorithm. A stack whose elements are monotonically increasing or decreasing. Okay, sometimes we store the index of the elements in the stack and make sure the elements corresponding to those indexes form the mono sequence. What does it mean for something to be monotonically increasing or decreasing? Does that mean every element is strictly increasing, or it's just greater than or equal to? If we need to pop smaller elements from the stack before pushing a new element, the stack is decreasing from bottom to top. Otherwise, it's increasing from. Right, that makes sense. What's this? If we need to calculate both next smaller and previous smaller arrays, we can do it using a monostack in one pass. Oh, this problem is related to largest rectangle in histogram, which is a problem that I've done before, but I'm pretty sure I needed hints and stuff as well to get that one. Similar questions. Oh, there's a next greater element question. So if we were able to calculate in constant time, because we pre-processed what the next greater element is, that would tell us like at which point this element stops being the largest element of the subarrays. Man, this is hard. I don't know. Okay, I don't know. I feel like I'm spending too long on this one. I think I'm going to study the solution and move on to a different problem. Here we go. Discuss. And this guy's on the top of like every fucking discussion page. Leet215. Okay, brute force is n cubed. We talked about that. N squared. This is basically word for word the code that I already wrote. Well, actually this, because I did it in C++. Then solution 2, the stack solution. Follow the explanation in 907 sum of subarray minimums. Intuition, the result is the sum of A sub I times F sub I, where F sub I is the number of subarrays in which A sub I is the minimum. Oh, okay. I don't know if my brain is quite ready for this right now. I kind of want to do something graph related. Hold on, let me just take a look at this. Okay, that topic does not exist. To calculate, so hold on, let me just see, what is left eye and right eye? The length of strict bigger numbers on the left side of A. Right, the length of bigger numbers on the right side of A. Then left eye plus 1 equals the number of subarrays ending with A sub I, and A sub I is the minimum. Bro, there's no way I would have to produce this in an interview, right? This is some like code jam shit. Well, I know it's actually not. Code jam is significantly harder, but here's what I want to do. Go back to the problems list. I'll take my n squared solution for that one. Anytime I get a green accepted badge, I'm like, good. All right, what do we have next? Sort by frequency. Reorder data in log files with 56% acceptance rate. Search suggestions system. That sounds interesting. Show problem tags. Oh, show problem tags. Okay. This is actually useful because there's some stuff here that I definitely need to review. For example, dynamic programming, which is in a lot of these. Yeah, reorder data in log files I think is a problem I've solved before, even though I don't have a green check mark here. You basically end up having to write like a custom sort function. Now count unique characters of all substrings of a given string. Count unique characters of all substrings of a given string. I mean, that one's labeled as hard, but it seems doable. What's this? Substring with the largest variance. Concatenate. No, you know what? I'm not gonna. I already struggled on the last problem. Let's try to go to something a little bit more reasonable for now. The K points closest to origin. Apparently, I did that. Array greedy and prefix sum. It seems reasonable. Shortest path to get food. Oh, here we go. Here's the breadth first search matrix problem. Let's take a look at that. Let's see if we can calculate the shortest path to get food. Hold. Hold. Sorry. Okay, you are starving and you want to eat food as quickly as possible. You want to find the shortest path to arrive at any food cell. You were given an m by n matrix, a character matrix grid of these different types of cells. The star is your location. There is exactly one star cell. Pound sign is a food cell. There may be multiple food cells. Uppercase O is a free space. You can travel through these cells. X is an obstacle. You cannot travel through these cells. You can travel to any adjacent cell north, east, south, or west of your current location if there is not an obstacle. Return the length of the shortest path for you to reach any food cell. Okay. So that does seem like pretty straightforward DFS. Or BFS, which means we would use a queue. DFS, you would use recursion. I think that there's like ways to do DFS with a loop, but I don't know how to do it. So first we need to know what our location is. So let's get this information first. So let's get n equals grid.size, and we'll get m equals grid 0.size. It's guaranteed, I suppose, that the grid has at least, yeah, m and n are between 1 and 200 inclusive. The grid contains exactly one star. So we need to know where we're starting. So for int I equals 0, I is less than n, plus I. I feel much more confident with problems like this. But honestly, that being the case, definitely tells me that I should be focusing on the other categories more. But I don't imagine having to actually produce a monotonic stack in an interview. But I could be wrong about that. Okay, so I goes from 0 to n, j goes from 0 to m. If grid ij is a star, then I start. We'll just do this. And then that's probably all we need to do here. We just need to figure out where we're starting. Oh, we need a double break. So I guess we'll just do if I start is greater than or equal is greater than -1 break. I mean, this is a optimization that doesn't really matter, but we just want to make sure that after we find the start location, we need to break out of both loops. Not really an important optimization though. Okay, so then what we need is a queue. So we're doing a breadth first search, not a depth first search. So a queue of pairs int queue. And the first thing we do is queue dot push. And I think I can do I start j start. I start j start. And then this right now what I'm writing is fairly boilerplate for a breadth first search. So while the queue is not empty, what we end up doing is doing a auto position equals queue dot front of the queue is what we want. Yeah, queue dot front, and then queue dot pop, right? Queue dot pop will remove the front element. C++ queue. Pretty sure that's the case. Okay, that looks right. Then we've got int I equals pos dot first, int j equals pos dot second. So now we've got those. And so now what we want to do is so the number of steps. Okay, so okay. I think the queue also needs to contain the number of steps we took to get to this position. That would be one way to do it. The other way to do it would be to use a 2D array to keep track of that. But that would use more space. So instead, this needs to be a vector of ints, start, and then the number of steps you've taken is 0, like that. And then I equals position 0, j equals position 1, int d for distance equals position 2, just like that. So if grid ij is a food cell, which is a pound sign, right? If grid ij is a food cell, then we're done. We actually return D. If it's not a food cell, then we need to look at the 4 spaces around us. And for the ones that are, I think that I can do this kinda 5-headedly. Here, let's do this. Let's get fancy. Switch grid ij. Let's get fancy. So we got switch case star case pound sign return D case obstacle. Oh wait, no, we don't want to do this. Like for we don't even want obstacles to be in the queue, ideally. So what? So forget that. We're not going to be fancy. So if it's a pound sign, we're done. If it's not a pound sign, we need to look at the position above, below, to the left, and to the right. There's like a nifty way to do that. Let's see if I can remember how to do it. There's like a, I've done this before. Int, so dd for like directions. Okay, dir. Int, we want an int array equals 0, or was it 1, 0, -1. I'll try, so if I can figure this out, I'll explain what this is in a second. Is that it? 1, 0, 0, -1, -1, 0. One zero, 0, -1, -1, 0, 0, 1. Yeah, this, I think this is it. So the idea is we need to look at the adjacent cells. So we need to do like I+1j, ij+1, I-1j, ij-1. And so what this little dir array, and I'm a little rusty on C++, so I might have to fix the syntax here in a moment. But it basically lets us take these the elements of this array like 2 at a time, 1 0, 0 -1, -1 0, 0 1, and these pairs here are what we're going to add to I and j to get like the next I and j that we're going to look at to see if we can move there. Let me return -1 down here and run the code, because I don't think the syntax of that is right. Okay, the syntax of that seems to be right. So the way that you do this is you do for int okay, I'm dir ddir, I don't even know, ddir, so we ddir is 0, ddir is less than 0, 1, 2, 3, 4. 4. Yeah, okay. That seems kind of obvious now that I calculated it. Plus ddir. So this is an iterator through that dir array. And what we basically get now is we get next I equals I plus dir of ddir. Man, my variable names are so bad right now. And then the next j equals j plus dir of ddir plus 1. And so essentially what we get here is just, it's kind of like, I just like coding it this way because it's shorter. And it's like a little cleaner. You just have like kind of a streamlined way just to look above, below, left, and right. We need to check that these are inbound, so if ni is less than 0 or ni is greater than or equal to n, we continue, or nj is less than 0 or nj is greater than or equal to m. So this just makes sure that the next I and the next j are actually within the bounds of the grid. Otherwise, we just move on to the next one. And then we want to do if the grid of the next I and the next j, it needs to be an open space. So it needs to be an uppercase O. If it is that, then we add that to the queue. So we do q dot push, and it's ni, nj, and then the current distance that we've traveled plus 1. And then there's another factor here, which is we don't want the code to take us around in like circles. So because we're doing a breadth first search, as soon as we put a element into the queue, like a coordinate set of coordinates into the queue, we want to make sure we never like revisit that again. So we turn it into an X, basically, is what we do. So the way we can do that is here, grid ij equals X, because we never want to return to a tile a second time. Because if we do return to a tile a second time, it's not the shortest distance, basically. The shortest distance is guaranteed to be like the first time we encounter a tile. So every time we look at a tile, if it's not a food cell, we just literally overwrite the value in the grid with an X, so that a future like iteration of this BFS while loop will not look at it. This also ensures that eventually, let's say that there's no solution to the problem, and we want to return -1. If that's the case, what we'll actually end up doing is every single reachable tile from the start tile will become an X. When that happens, new tiles will stop being pushed onto the queue. The queue will become empty, and then the program will come down here to line 49 and return -1. Run code. Okay, so ran the code, we got wrong answer. We said it's -1, but it's actually 3, so something's not quite right. 1, 2, 3. RJD. If ij is asterisk, then we have our I start and our J start. Okay, so now we're in debugging mode. I'm pretty positive I just did something silly, so I gotta try to figure out what it is. Okay, so 1, 1. That's correct. Oh, is the border of the puzzle guaranteed to be surrounded by X's? Because if so, I don't need to do my boundary check. Okay. Yeah. So the problem description doesn't guarantee that. So I'm pretty sure I need to do the boundary check. So we are correctly finding the start tile. So let's see what we get here. I, J, D. So we'll just output where the BFS is going. Okay, so we start at 1, 1. We got 1, 1, 0. Then we go to 2, 1. Two, 1 and 1, 2. So it looks here and here, which is correct. Then 2, 2 and 2, 2. Oh, that's actually kind of obnoxious. This coordinate does get added to the queue twice. 2, 4. Which we can fix. We can fix that. We can fix that here. Or grid ni nj equals x. So we'll just move. Oh, you know what? We didn't actually check that. And then we do, okay, yeah, and then I'll move this logic, I'll move it in here. So basically, it's not possible for two tiles that are adjacent to the same open tile to both add it to the queue. But now the problem is, if we overwrite the tile with an X before we visit it, we're actually going to end up overwriting food tile with X's. So we need to check for the win condition, the victory condition or whatever here. So ni nj, if it's £, then we return d+1. So we can get rid of that. The other thing that I can do is, after I discover where the start tile is, I can change it so that it's an X. How am I doing now? Okay. That's actually the worst possible way to solve a bug, is to just make improvements to the code that you can see without understanding which of the improvements you made was actually the issue. But that's literally what just happened. Anyway, submit. Accepted. Runtime 383 milliseconds, faster than 7.06% of C++ submissions. That's kind of sad. Why are we so slow? Why are we so slow? Oh, is it because it's because I'm printing to the console? There we go. So we just removed some C outs, and we get 53.97%. All right, cool. So we solved this problem. Submit it without those lines of code. Let's just, I mean, this one is marked as a hard problem, but let me just read the description to see how ridiculous it is. You're given an m times n integer image where each cell is either 0, empty, or 1 obstacle. You can move up, down, left, right from and to an empty cell in one step. Return the minimum number of steps to walk from the upper left corner to the lower right corner, given that you can eliminate at most k obstacles. If it's not possible to find such a walk, return -1. Okay, that's interesting. I need to take a quick bathroom break. I'll be back in a minute. I'll think about that while I'm doing it. Okay, I think I know how to do this one. It's actually very similar. So it's extremely similar. We still have to do the BFSQ, but in addition to storing, so in the previous problem, what we put onto the queue was the coordinates I and j along with the current distance from the starting point. In this problem, we add one more element to the queue, which is the number of obstacles that we can still remove for this particular path. Is that gonna work? How do we make sure we don't go back? Because in the last problem, we made sure that we didn't backtrack by turning any open cells that we visited into closed cells. In this problem, do we still do that in this problem? I think we can still do that in this problem, except we need additional information. Like, if we change a open cell into a closed cell, because we visited it, we need to make sure that we don't then try to remove that cell that we visited and you know, because we have k obstacles that we can remove. Okay, this seems reasonable. This is going to be pretty similar. This will be the last BFS problem I solved today, and I'll try to move on to a different category after this. Okay, so similarly, int n equals grid.size, int m equals grid 0.size, similar to the last problem, I assumed that the size of m and n is at least 1, and it is. We know that I start equals 0. We know that j start equals 0. We know that I end equals n minus 1. We know that j end equals m minus 1. So we know all that just from the problem description. So it'll be nice to just have those in variables so that we can reference it easily and it'll read easily. Okay, so we're gonna have a queue of vectors of integers, q, and it's gonna be I, j, d, and k, which is the remaining number of k. So first thing we push onto the queue is we push on I start, I end, j start, 0, and k. K is the number of, in the case of what's on the queue, k represents the number of remaining obstacles we can remove, because we're going to be removing obstacles along the way. So every time we remove an obstacle, we'll just decrease k by 1. And the grid is all zeros and ones. We're probably going to have a 2 in the grid for this implementation to work. 2 will represent a visited tile. So basically, if we're at tile ij and we're looking above, below, to the left and to the right to see where to go, we're not going to move into a visited tile, but we will move into an obstacle tile, assuming that k is not 0. That's what we're going to do. Let me rename this to max k, because I want to use the k variable in my BFS loop, k max. K max. So similarly, while the queue is not empty, we're going to do all the very similar to what we did before, and at the end, if we weren't able to find a path, we return -1. Also very similar to what we did before, int dir is going to be 1 0 -1 0 1. I won't explain that again, other than just by saying that it's going to enable us to look up, down, left, and right really easily in a loop. So auto current equals q.front. Failed to retrieve suggestions? Why? q.pop. Have I done something wrong here? Oh yeah, that's what's wrong. I need that there for the syntax to suggestions to work. Then int I equals current 0, int j equals current 1, int d equals current 2, and int k, the remaining k, is current 3. So these lines of code they're just pulling the specific information that we're storing in the queue back out again. So now what we want to do is we're going to look around in all the directions again. So I'll try to write this code the same way I did for the last problem. So int ddir equals 0, ddir is less than 4 plus plus ddir. So now what I'm iterating over is basically the I and j diff, or the I and j delta for looking up and down. So we get int next I equals dir equals I plus dir of ddir, and then int next j equals j plus dir of ddir plus 1. Probably this is the most confusing part of the whole implementation, I think. Well, that and having the k on the queue. But we're basically gonna add 1 0 to ij. We're gonna add 0 negative 1 to ij. We're gonna add negative 1 0 to ij, and we're gonna add 0 1 to ij. And because of that, we're gonna go up, down, left, right. So similar to the last problem, if next I is less than 0, or next I is greater than or equal to n, or next j is less than 0, or next j is greater than or equal to m, continue. And then also for visited tiles, we don't want to consider those either. So or grid of next I, next j, if it's 2. Now that's interesting because if you look in the input, it's not possible for it to be 2, but we're going to be, as we visit tiles, like the first time we visit any tile is the shortest distance to the tile. That's just how BFS works. So if we visit a tile again, it's automatically not the shortest path. So what we do is every time we visit a tile, we're going to change it to 2 so that we don't come back to it. So now that we made sure that none of those things are the case, we're not out of the bounds of the grid, and we have not visited the tile that we're looking at. So I'll do one more thing here. I start, j start. So I'm going to update the starting position to be 2 because we don't need to visit that again. If grid ni nj, it's if ni equals I and nj equals jn, then we're done. We found the solution to the problem, and it's d plus 1. D being the distance that it's taken us to get to the current tile. So we're returning d plus 1. Yeah, so that's good. The other possibility is that, now we have 2 possibilities. Ni could be a 0, or Ni could be, grid Ni and j, the next tile, could either be a 0 or it could be a 1. If it's a 0, we move into it, but we don't need to decrease k, because we don't need to remove an obstacle to get there. If it's a 1, let me make sure I got this right. 0 is empty and 1 is obstacle. If it's a 1, we will move into it, but only if we have enough k left to do so. So if grid ni nj equals 0, we're going to move into it. And we're going to mark it as visited by changing it to a 2. Yeah, this will work. This will work. So q dot push. Why am I not getting autocomplete here? Is there a syntax error that I don't know about? Run the code. Put a break statement here. Run the code. Oh no, there's no syntax error, just autocomplete's not working for some reason. Okay, that's fine. So if it's 0, then we can move into that tile, that cell, without needing to remove an obstacle. So what we do is q dot put, oh now it's working, okay. Q dot push, and it's going to be the next I, the next J, distance plus 1, and K. And then since we're going to be moving into it to further explore that path, we then update, we mark it as visited. Whoops, didn't mean to open the DevTools. So grid ni nj equals 2. So at this point, we can just do else, because there's nothing else that grid ni nj could possibly be. We know it's not a 2, we know it's not a 0, so the only other thing it can be is a 1, which is an obstacle. If it's an obstacle, then we push onto the queue the exact same thing, except it's k minus 1. Oh, like that. This line of code can be shared by both of these blocks, so I'll move that out like so. And I did just notice one bug that I introduced, which is if the cell that we're trying to move into is 0, we can just go there without having to change what k is. We just increase the distance by 1. However, if the grid is 1, which is this else statement, it's still possible that we can't move there if we have exhausted k. Else if k. So that'll fix that. So k needs to be at least 1 in order for us to move into the cell that's got an obstacle in it. So yeah, this will do that. I could write it like else if k is greater than 0. I'll probably just write it like that for readability, but just doing if k there would essentially do the same thing because of how Boolean logic works in the language. What else? Is that it? What happens if we run this? Ooh! So we got accepted for the first test case. Let's try to see what do we get for this puzzle. Oh, this one's supposed to be -1. Okay. All right, I am gonna submit this. I feel decent about this approach, this solution. Let's submit. Wrong answer. Oh, really, dude? It's the most frustrating part of this is like you get a solution that's right, but it doesn't take into account like a silly edge case. So, yeah, so literally all we need to do is this. If n is 1, and m is 1, return 0. I'm pretty sure that that's all we need to do there. That at least will handle this test case. So I needed to, because of the way my code is structured, I needed to specifically handle the case where they give you a 1x1 grid. I think it's gonna get accepted now. Oh, okay. All right, so we actually have a reasonable test case that we failed. So let's take a look at this test case. So we're not far off, but there's something wrong with the logic of the code that we went 2 steps farther than we needed to get to the answer, to get to the bottom right. So I'll just run this just so that it's going to say the same thing. It's going to say, yeah, expected 14, but I said 16. Interesting. So that could mean that I have some kind of small logic error in my solution, or it could mean that my approach is way off. Not entirely sure which of those two it is. This is an interesting grid. So it's got 5 obstacles, then I have 3 obstacles. I said it takes 16, but it actually takes only 14. Interesting. That's not ideal. Hold on. I gotta correspond to text messages real quick. Okay, sorry, I'm back. Wait, am I back? I might not be back yet. Okay. My friends are asking if I wanted to play Stick Fight tonight, which is an amusing game that I do enjoy playing. So I told them, very non-committally, to put me down as a solid maybe. Okay. So, what's wrong here? Do I have just a simple, like, mistake that I'm overlooking? Or is there, like, a major flaw in my approach? So this grid, man, I might have to get Microsoft Paint open. Let's do it. I don't have really good charting or software or anything like that, so we're gonna get Microsoft Paint. And you're not going to be able to see it, so let me just make it so that you can see it. Okay, that works. So the grid that they gave us is oh man. I'm gonna have to get some better software for doing stuff like this. Zero, zero, 1 0 1 0 1 0 1 0 1 0 0 0. This is really next level technology right here. Then 0 1 0 1 0 1, then 0 0. I'm gonna add the ones in later. Then 1 0 1 0 0 0, 1 0 1 0 0 0. Okay. So k is equal to 4, right? K is equal to 4. So we're allowed to remove 4 obstacles. So what I'm thinking is we start... You can see my cursor? Can you see my cursor? We start here. We start here. We remove an obstacle, we remove an obstacle, we remove an obstacle, we remove an obstacle. No, that's probably not right. Well, no, it might be right. So that's our 4 obstacles removed. So then we have to come here, 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 here. That's what I assume the answer is. How many is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Oh, wow. That is not the optimal answer. Oh, you know what? You know what? I see it. I see it. It's gotta be 1, 2, 3, 4, 5, 6, 7, 8. Remove obstacle, remove obstacle, remove obstacle. 9, 10, 11, 12, 13, 14, 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Oh, wait, no, that's 14 because you don't count the starting space. So that's the correct solution, is to remove 3 obstacles on that second column. And I'm able to see that just with my eyes. So why is my program not coming up with that as the solution? Let me just read through the code, see if there's anything really glaringly obviously wrong. So n is grid size, m is grid 0 size. If it's 1 1, we return 0. I start 0 0, j start 0, I end n minus 1, j end m minus 1. We have the vector, the queue of vectors that holds ij dk. We start off at I start and j start. Distance is 0, and k max is the maximum number that you're allowed to remove. Is that right? Let me switch back to the other thing. You guys can't see what I'm doing. We mark the starting spot as visited. Then while the queue is not empty, we grab it. We do I, j, d, k, 0, 1, 2, 3. Then we go through the dir array, 1, 0, negative 1, 0, 1. That's right. next I is I plus dir dir, next j is j plus dir dir. That's right. Ni less than 0, or ni greater than or equal to n, or nj less than 0, or nj greater than or equal to m, or grid ni nj equals to continue. That's right. If the next I is I end and the next j is j end, we return the current distance plus 1. That's right. If ni nj is an open tile, we move into it without decreasing k. Otherwise, and the only other possibility here is that grid ni nj is a 1, which means it's blocked. If that's the case, then k needs to be great. I think this logic is right. Yeah, this should be right because the grid of ni and j can only be 0, 1, or 2. We already know that it's not 2, so we continue. Then we check to see if it's 0. If it is, we move into it without changing k, and we increase the distance by 1. So then we hit this else block. The only time we can possibly come to this else block is if grid ni and j is equal to 1, which means it's an obstacle. In that case, k needs to be greater than 0 for us to move into it, right? Let's just double check what k is. K is, yeah, you can remove at most k obstacles, all right? Then we do ni and j d plus 1 k minus 1. And then last but not least, for both of these if statements, we want to mark the position we're going into as a 2. Okay, so I might log here, honestly. I don't know what else to do. I, J, D, K. I'm not quite sure what else to do. So I'm going to remove these other test cases. And we're only going to look at the one that I'm failing. And let's run it. We get wrong answer, but I'll be able to see what the code is doing. So 0004 is correct. Then we go down to 1013, which is correct. We also do 0114, which is correct. Then 2022 is correct. Oh, you know what? I see what the problem is. It's possible to get to a tile 2 different ways with 2 different values of k. Like for example, this tile right here. Can you see my cursor? Oh wait. Let me go back to paint. This tile right here, it's possible to get here 2 different ways with 2 different distances and 2 different k values. So the way that I'm marking the tiles as visited is not particularly right. Because like I could, for example, I could go boop, 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 boop. Like let's say that k was higher than 4. I could go all the way down to this tile, and I would get to this tile with distance of 6 and k of 0, like let's just say that we used all of our k. But I could also go around and get to this tile and still have all of my k's left, which could be the optimal solution to the puzzle. In this case it's not, but this is just an example. I like this test case actually, because I think they included this test case to help people discover the exact bug that I'm having. This test case makes it fairly easy to see. So marking the cells with 2 to make sure that you don't re-enter them is actually wrong. That's not what we need to do. Instead, what we need to do, I think, is store the distance that it took to get to each cell. And then if I encounter a cell again, I only move into it if I've got a shorter distance than what's previously there. Which is, it's kind of a little bit more Dijkstra-y, but it's not Dijkstra, it's still just BFS. Dijkstra is like a glorified BFS. Okay, I think what I do here is, so I could make a whole nother 2D array to store the distances. I don't think I want to do that. I kind of want to just keep using the original grid to store all my information. So I'm going to use negative numbers to represent the distance. Something like this. That way it's still constant space, rather than linear space. I mean, it's probably not an important optimization in this problem, but I'm going to do it this way anyway. And the starting spot will be -1. Okay, it needs to be d+2. So basically, negative number is the distance, but it's 1 lower than what it actually represents. Okay, so here's what I need to do. I now need to have a special case. I'll do it down here. I'll have if grid n, ni, nj is less than 0. That means that we visited this tile before. But it's possible that right now I'm getting there with a shorter distance. Wait, now is this gonna work though? Ah, okay, I can see why this problem is marked hard now. Hold. No, I finished all my water already. Okay. I'm thinking. The main issue is we don't want to be going back in circles, but we do want to be able to visit cells again if it's with a shorter distance than what's already there. But what if it's with a longer distance? That might actually be okay though. That's the thing. It might actually be okay. Hold on, let me undo these changes. I don't think this is quite what I want to do. Pardon me. Okay, do I need to mark the tiles as visited? What happens if I... Just theoretically speaking, if I were to not do this, if I were to not do that and not do this and not do this, what does the program say the answer is? Okay, so that actually gets me the correct answer. But I don't think this is going to work for a large test case. I bet if I submit this, I get time limit exceeded. Because even though eventually, maybe in a really long time, it will come to the right solution. Wait, will it? No, it might not. Oh, that's not even that large of a test case, look. No. So my code now is effectively an infinite loop. What's the max value of K? Oh shit. I'm still on fucking paint. The max value of K is m times n. Oh, okay, so basically what they're saying is the solution could just be to remove every single obstacle in the way and go down and to the right. But m and n are both less than 40, which means that K has a maximum value of 1600. So do I need a 3D array here where for every single cell in the grid, I also store what the shortest distance for every possible K is? Let's check out hints. Hint 1, use BFS, thank you. BFS on XYR. I am doing that. Related topics, yeah, breadth first search matrix, we know. Minimum obstacle removal to reach corner. That's actually an interesting next problem, but I haven't solved this one yet. So when you visit a tile, So, okay, let's think about it this way. When do you not want to revisit a tile? So if you're looking at the 4 adjacent squares and you're trying to decide if any of them are worth pushing onto the queue for further examination, you do not want to revisit a tile if you've already visited it with the same K, right? So, okay, let's explore that. Let's make another 2D grid. So we'll have a vector of vectors of unordered sets. Of int. And so what I'm thinking now is for every single coordinate, we keep track of which k's we visited that coordinate with. Visited. How do you, okay, there's a way to like initialize these with a size, right? Visited n and then vector of unordered set m. Is that right? Let's just run the program. Unordered set of ints. Yeah, okay, so that should work. So visited I start J start. Oh wait. We don't want to visit a cell if we visited it with the same K or any greater Ks. Like the greatest K that we visited a cell with is the one that we want to keep, right? Is that right? The greatest K that we visited a cell with, because that means that we have the maximum number of Ks left for other obstacle removals. So if you come to a cell and you got like K10, but you see that you've previously visited the same cell with I think this will, let's just try this. I don't know if this is gonna work. Insert. And then here, or visited ni and j dot count let's just, hold on, it's getting a little hard to read here. Space some of this stuff out a little bit. So here we're just checking the bounds, here we're checking to see if we're done. So if it's open, we don't need to change K. And we haven't visited it with this K. And we haven't visited it with K minus 1. Visited ni nj dot insert K. So I think what I'm trying to do here is set a strict upper bound on the number of times you can possibly visit a cell, and it's going to end up being all the different values of K, which can still be a lot. It could be 1600. So you could, I guess, potentially, theoretically, in a worst case scenario, you could end up visiting each cell 1600 times, but it's probably not the most efficient. I'm trying to see if I can get this to be accepted. There it is! We did it! Oh, I wasn't sure I was gonna get that one. It's slow. I'm faster than 7.5% of other C++ submissions. And I'm only using less memory than 7% of C++ submissions. However, it is accepted. Let's submit it a few more times, make sure it wasn't a fluke that it was accepted. Okay, that time the running time went down significantly, so half. But still slow. Okay, so it's definitely accepted, right? I submitted it 4 times and I'm getting accepted. It is slow. It's faster than 10% of submissions, but it's. I like to think that I have a solution that's at least above average, and so for that you want it to be faster than 50% of submissions, which it's not. But I'm just happy to get this accepted. So let's see if so now that I know this works, how can I optimize this even further? So what I'm doing here is, if you come to a cell, you only move into it if you haven't moved into it with that same K before. But would you want to move into it if you have a lower K than before? I don't think you would, right? Like if you visited this cell and before with a higher K value, what that means is that the previous time you visited it, you had more obstacles left that you could remove. Okay, so I got it accepted. So let me just see if I can tinker it with it a little bit more. And it'll actually make it use way less memory too. This actually just becomes this just becomes a vector of ints. Those will all get initialized to 0, right? C++ initialize 2D vector. I might have to do like a fill or something. Oh, default value. There it is. So the default value is -1, indicating that we've never been to the cell before. Then here, visited iStart JStart is going to be kmax. Then here, visited ni nj is great. So we only want to move into it if the previous time we had less k. So if this is lower than k. That seems right. This one is visited ni nj, I feel good about this, is less than k-1. Because of the way BFS works, every single time we visit a node, it's the shortest path that we've found to that node. I think this is going to work. I don't know if I could verbally prove it properly, but I've got a good feeling about this approach. Visited ni nj equals k, meaning that we're visiting this node now with more k left. Visited ni nj equals k-1. Let me get my other test cases back as well. I'll drop those in here. Okay, so we're still getting 6 -1014, submit. There it is. There it is. I'm very happy with that. That is a fast solution to the problem. So you're doing a normal BFS, but you're keeping track of, every time you visit a node, you're keeping track of how many K you have left, K being the number of obstacles you can still remove. If you want to move into an obstacle, you decrease K. However, we don't want to revisit nodes needlessly, so we keep track of what the best value of K is that we've had for each node that we visit. And when I say the best value of K, it's the highest value of K, because you don't want to revisit a node with less K than you did before, because that means that not only is your distance potentially greater, but you also have fewer obstacles left that you can remove. So we only move into a tile if the new K is going to be higher than the previous one. We submit this, we get a runtime of basically 10% of my previous runtime. Also significantly less memory. We're faster than 60% of C++ submissions, and we're using less memory than 56% of C++ submissions. Let's submit again and get a couple more runtimes. Yeah, so it's the running time is in the like 60 to 90 millisecond range. The number of memory each time is about the same. So what I like to do at this point is, well, first I want to remove the comments. It was just the one. I'll submit it again without the comments. It's not going to make a difference. So what I like to do now is, now that I've solved that problem and I feel good about it, and I know that I have a pretty like optimal solution, like I'm not going to go through the effort of like micro optimizing this to try to get like faster than 100% of submissions. Some people enjoy that, and more power to them. I'd rather just like come out of the problem knowing that I wrote an efficient solution to it. I don't need to know that I've written the most efficient solution of all time. So now that I've done that, I'm happy with my solution. What I'm going to do is actually read, or at least browse through a little bit what the recommended solution is, which I expect in this case for this problem is going to be fairly similar to what I came up with. So So yeah, first of all, intuition, we don't need to read that part. Then the algorithm, we would employ a queue data structure. Yep, however, in our problem here, we did another piece of information, which is the remaining quota. Together with the coordinates, the obstacle elimination quota uniquely constitutes a state. Yep, so we did all that. Implementation, blah, 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 blah. Break down the algorithm, a loop around the queue, as well as a set scene which keeps track of all the states visited along the way, so we don't visit the same state twice. Oh, that's interesting. That's interesting. I didn't think of that. But you still run into the issue of potentially revisiting nodes with a worse K than you did before, I think, with this. Unless they probably take care of that in the solution somehow. So basically, scene is just going to be like it can't be well, no, it could be like an unordered set of like the state of the BFS. So it would be like all these numbers combined into a single number, a single unique number representing these four, and throwing that into like an unordered set or a normal set. So let's look at the solution. Let's look at the Java solution. No, let's look at the Python solution. So we got that. We got the target equals rows -1, columns -1. Shortest distance is the Manhattan distance. Okay, interesting. So this if statement right here is probably a better way of doing what I did here. Yeah, it is a better way, but that's fine. I wonder if I threw these lines of code in there, like how much faster my average runtime would be, but I'm not going to do that, I don't care. So the state is 0, 0k. Okay, so that, well, interestingly, they don't store the distance in the BFS like state. I do that. How are they keeping track of the distance? Zero K. Oh, so row call remaining quota. Oh no, they are doing it. They're just like combining the state into a single thing instead of having it instead of having like a 4 tuple with all of it. They have a 2 tuple that has a single integer and a 3 tuple. And then yeah, and they're just doing that so that they can use this set of scene. Reach the target, return steps, explore the directions. Yeah, so this seems like a pretty straightforward Python way to do what I did here with the dir array. Right, is making sure that it's in the bounds. New eliminations, k minus. Grid new row, grid new column. Oh, I see. Because grid new row, grid new column is just 0 or 1. So if it's 1, they're decreasing k by 1. That's kind of, yeah, that works well. A little more difficult to read though. New state, new row, new column, new eliminations. Add the next move in the queue if it qualifies. I see. Okay, so they only go into the queue again if they haven't seen this state before, and the state is I, J, and K. And so this is actually, this seems like my original solution, which was slower. But I'm not too sure. I'm not going to analyze it too hard though. Time complexity, n times k. Yeah. So n times k was my other time complexity, where my visited grid was a grid of sets of all the k's that had visited that cell. My time complexity now is just n, because I have a second grid that's just a grid of integers. So A star algorithm. Okay, then they use the A star algorithm, which I'm vaguely familiar with. The idea behind the A star algorithm is, instead of just blindly going, like, kind of expanding out in a circle around the starting point, you use the idea that if you know where the target is, you can kind of tend in that direction. So like this diagram represents it well. So you do still need to go like up and to the left, but it's more likely that going down and to the right will get you to the solution faster. Now, obviously, like going down and to the right could be completely surrounded by obstacles, right? And you might not have enough K to remove those. So eventually, you'll still have to go up and around. But you know, depending on like the type of data you're dealing with, the type of input, you probably, in the average case, for like normal input that's not intentionally built to fool your A star algorithm, you'll get there faster. So the running time of their A star algorithm is n times k times log of n times k. That's slower, dude. Yeah, okay, I see. Yeah, so they're actually, so this is the worst case, I guess. So in the worst case, A star can actually perform worse, is what they're saying here. But on average, the A star will outperform the BFS approach if there's any relatively direct path from the source to the target. That makes sense. So, and then the space complexity is still n times k here. So, is my solution better than that? Well, my space complexity is definitely better because I don't have a space complexity of n times k. But probably more importantly, my time complexity is just going to be n times k. That's funny. If you really want to get a fast, runtime, basically solve the problem incorrectly, and because there's a test case that doesn't check it. That's funny. Hash code and equals concept. Oh, okay, that's smart. Yeah, let's just take a look at that real quick. So in the Java solution, obviously it's the same. They're using the set. So the hash code is row plus 1 times column plus 1 times k. Really? There's no conflicts with that hash code? Well, anyway. I see. That's cool. So they made a little class to encapsulate the state, and they overrode some of the the built-in Java functions, so that Java knows how to basically compare two states to see if they're the same. So that's smart. I like that. I mean, it's a lot of code. Like, you probably wouldn't want to write it this way in a contest or something like that. Honestly, in a contest, being able to just throw like tuples into a Python set, that's really fast. It's really fast to code, you know, even if the running time maybe is not as good. But yeah, that's cool. All right, so I'm happy with that solution. I think my brain might be done with coding for now, so let's just go take a look here. As you can see, I haven't done LeetCode for a long time. Let's look at 2020. So in 2020 was when I was preparing for interviews at Google. Oh, what's up? Easy game, easy life. Mind checking out a small project of mine. It's a website that can generate code from a text description. Could be interesting also for LeetCode. Yeah. Paste a link. I don't mind taking a quick look at it. I was just looking at my my LeetCode history here. So in 2020, I was doing some serious interview grinding for like 4 to 5 months. So I have a lot of activity. And then after I finished my job search, I just started not doing basically any LeetCode. I don't know what happened here. I guess I had a small little time period where I was doing LeetCode, and then like now, kind of getting back into it a little bit. Thanks for the follow too. Oh, I just realized this was all 10 minutes ago. I'm sorry. I don't even know if you're still here, but I was in the zone. Anyway, how many problems did I solve today? I solved 4. It's somewhat of increasing difficulty. The last one was a hard problem with BFS. Glad to have knocked that one out. There's other types of problems that I need to review, so I'll probably be doing streams like this where I'm reviewing. I need to review dynamic programming, other types of graph problems other than the ones we looked at today. What else? String stuff. I don't know. There's like a bunch of stuff that I need to do. What does this graph mean? Does this mean I'm in the top 7% of users? Oh, I am. That's kind of cool. Oh, you know what? Maybe I should just take a look at the July LeetCode challenge real quick. But yeah, my brain's a little fizzled out now, I think. I can only do so much LeetCode per day. Let's take a look here. Featured. Don't they have, they usually have like a monthly challenge, right? I wanted to take a look at that. Just Google it. LeetCode July challenge. Yeah, but how do I get to it though? July LeetCode challenge. No, not from 2021. My buddy Larry, he's still doing like daily coding challenges. Okay, oh wait, maybe I have to go to problems to get there. Problems. Oh, they got a study plan? That's cool. Ultimate Dynamic Programming Study Plan. That actually sounds really useful because dynamic programming is, at least for me, has been one of the more challenging like concepts to really wrap my head around for these types of challenges. Oh man, I'm sorry that you came in, you sent a message, and then you left, because I probably didn't answer you because I was focused on the code. So what I'm gonna do is I'm gonna send you a whisper. Let me just do that right now, just to let you know that I did see what you said. Easy game, easy life. Let's see, whisper. Easy game, easy life. Okay, I found you. Thanks for stopping by the stream and following. And sure, feel free to send over your link. Okay. Really do appreciate the follow. This is a brand new channel. Other than a follow from my other channel where I play video games, you're the first follow, so I do appreciate that. I don't think you're here anymore, but I'm saying that anyway. But that's gonna be it for now. I'll be back tomorrow with another LeetCode problem solving stream. And yeah, so anyone who happened to be here, who was watching, appreciate it. Thanks for stopping by, and I do expect to be streaming a very similar stream to this again tomorrow, because I need to review some of this stuff. I've got interviews coming up, which is part of the reason I'm doing this. So, all right. Thanks everyone. Bye.